Okay, hello everyone. In this video, I would like to show you how to create a model of a water distribution network using OpenHydroQual. So the diagram that you see is our basically shows our water distribution network that we want to model. I'm going to go over the components first. So basically, we have a storage tank. The properties of the storage tank is given. Its base area is 100 square meters, and then it has an elevation of 20 meters. The model consists of, or the network consists of six nodes. So the nodes are shown using the circles. Their elevation are given. They're numbered from 1 to 6. And then we have consumers that are shown using these house icons uh, that are basically withdrawing water from these nodes. Basically, and then I'm gonna assume that demand of each of the consumers is constant and is 1,000 cubic meters per day. Just one thing to point out, actually, to keep things simple, I'm gonna assume a constant water demand by the consumers, but you can easily change that and replace that constant demand with time variable demand if you provide the time series representing the time variation of the demand. The properties of the pipes are also given, including the length and the diameter. Now, this plugin of OpenHydroQual that I'm going to use is basically uses the Hazen-Williams equation to calculate the head, basically head drop versus flow rate in the pipes. I'm going to assume that all the pipes have a Hazen-Williams roughness coefficient of 100. Then we also have a pump that supplies water from a source to our storage tank, and the characteristic curve of the pump is also given. Basically, it's going to be based on this equation that you see. Okay, so let's get it started. So I'm gonna go to I'm gonna start OpenHydroQual, and then basically let me move this away. So what I'm gonna need to create this model is this plugin called basically tank pipe pond or something like that. So basically it's actually this plugin right here. It's called pipe slash pump systems. So I'm gonna add that to my uh, graphical user interface, and basically what that will give me is basically it gives me these two kind of nodes or junctions. We have this rigid junction, which is the one that we're going to use, and then we have this elastic junction that we're not going to use for some reasons. It's not going to work out for this case. And then we have user, uh, which we're going to use, and then we have of course some connectors. We have a pipe, which is a kind of, it's called pipe Hazen-Williams equation two-way. That's the one that we're going to use. And then we have a pump. Now we have some other components that you might want to use. We have this one-way pipes. Basically, these pipes only allow flow to go from one node to another one, but not the other way around. And then we have these pumps with time series control. This is when you have a pump, but you want to be able to control the hydraulic head or things like that. So let's get started. And by the way, one of the other components that we're going to use is this tank. I forgot to mention that one. So basically, let's add our tank first. So I'm going to just click on tank. It'll add this tank component to my model. I need to go back and forth to the diagram to get some of the information. So what I know is basically the area of the tank is 100 square meters, and the elevation of the tank is 20 meters. So basically what I'm going to do is that I'll say the bottom elevation. Let me expand this so you can see the name of all the properties. So the bottom elevation is going to be 20 meters. The base area is going to be 100 square meters, and then I'm gonna assign some initial storage to my tank too, because what I want to do is that I want to be able to run the model before adding the pump to just test and make sure that everything works. So basically, I'm gonna add an initial storage of 100 cubic meters. Now, keep in mind that this is actually a small tank, and then 100 square meters is actually not a lot of water considering the usage that we have. So this amount of water is going to last for maybe a few minutes, considering the fact that we have these six consumers, each of them consuming at 1,000 cubic meters per day. Okay, so now let's start adding the nodes. So I'm going to use this rigid junction. I need six of them, and I'm going to order them based on the way it is in the diagram. So let me make sure. So basically we have two here, then we have three, and then we have one right there. So basically I'm going to have, this is number two, and then I'm going to have a number three right here. Let me just make sure that I'm doing that right. So basically, yes, number 3, 4, 5, and then 6. So basically another one goes here, another one goes here. And then let me make them a little smaller so that they look more like nodes. So I'm going to make this a little smaller too. Okay, then, oh, by the way, I need the sixth one, which I think I forgot. So let's see, this is going to be our sixth node. Then, so let's assign the properties of the junctions. The only property we need is elevation. So the elevations are basically what we have is 15, 12, 11, 8, 5, and 2. So I hope I can memorize this. So it's going to be 15 meters, 12 meters. Oh, this was not entered, so let's do 15. I need to press enter, and then we got 11, and then I think it was 8, 5, and 2. So basically we're gonna have 8, 5, and then 2 meters. Okay, so then let's now what I'm going to do is that I want to also add the consumers. So this is the consumers. I'm going to need 6 users. So basically that's going to be 1 right there, and then we're going to have another one. I'm going to place it here. Then let's do another one right there, and another one that I'm gonna place right by this node, and then let's do another one which goes here. And the last one goes right there. Okay, so now in terms of the properties, all I need is to specify the constant use rate for all of these. So basically we have two properties for the use. We have a use rate time series. I can introduce a time series file here that will give me the time variation of the use, and then we have a constant use rate. If I have both of them, the use is going to be the summation of the two. In this case, I'm just going to assign a constant use rate, so I'm going to just enter the numbers here. And what I know is that the consumption rate, the demand is 1,000 cubic meters per day. So I'm going to enter 1,000 right there, and then I'm going to pick other users, and I'm going to assign this 1,000 cubic meters per day consumption. So that one is going to be 1,000, and that one is going to also be 1,000. Okay, one more thing that I need to do is that I need to connect the users to the nodes, so to actually the corresponding nodes. So what that says is that I want to indicate that the a user is taking its water from a specific node. So in order to do that, I'm going to use this link called flow link to user. So I'm going to pick that one, and then I'm going to connect uh, sometimes if I click twice it gives me a hard time, so I need to inactivate and then activate it again, so then I can connect this. I'm gonna connect that one and this one. Oops, sorry, I did it the other way around. It has to go from the junction to the user, the node to the user. So basically, let me select that one again. Okay, so that's one, and then one more for this one, and another one for this one, and the last one is going to be from junction number 6 to residential user number 6. So now we have all the nodes connected to the users. Now we want to do the piping. Basically, so I'm going to connect, the way my network is configured is that I have a connector from my tank to junction 1, and I have also one from the tank 1 to actually junction 2, and then let me check the diagram. So I have from junction 1 it goes to junction 3 and 4, and then from junction 2 it goes to junction 4 and 5, and then both 4 and 5 are connected to 6. So basically junction 1 goes to, oh, I need to pick the pipe, so it goes to here, and then this one goes to here, and then what I'm gonna have is that I'm gonna have this one here. I can kind of drag these so that the links don't entangle with each other. So then I'm gonna have this one that goes to a junction number 5, and then lastly junction 5 to junction 6, and junction 4 also to junction 6. So this is going to be our network. Okay, now what we need to do is we need to specify the properties of each of the pipes. So let me go back and look at my diagram. So what we have is the pipe connecting the tank to node number 1 has a length of 200 meters and a diameter of 15 centimeters. So basically I'm just gonna pick this, and then the length is 200 and the diameter is, I'm gonna go with 0.15 meters. I can also say 15 centimeters by basically picking the right unit, but I'm just gonna keep everything in meters. And then I'm gonna keep the Hazen-Williams coefficient as 100, which is what is specified in my problem specification. So then the next pipe, it has a length of 100 and a diameter of 15 centimeters. So the length is going to be 100 meters and the diameter is going to be 0.15 meters. Then the next pipe is this pipe, so the length is 100 meters and the diameter is 12 centimeters. So the length is 100 meters, the diameter is 0.12 meters. The next pipe, it has a length of 100 meters and a diameter of 10 centimeters. So this is going to be 100 meters and the diameter is going to be 0.1. And then the next one is 100, 10 centimeters, and then 120, 15. I'm going to try to memorize that. So this is going to be 100, and it's a 10 centimeter pipe. And then this one is going to be 120 meters. I guess it was 15 centimeters. 0.15. The next one is is a 140 meter pipe with a diameter of 10, and then a 100-meter pipe with a diameter of 10. So this is going to be 140, and the diameter is going to be 0.1, and then this one is going to be 100, and the diameter is going to be 0.1. So the diameters are fixed. Now let me save the model. So I'm going to click save, and then I'm going to save it in this folder, and I'm going to say pipe network tutorial. So now actually what I can do is that I can run the model. What happens is if I run the model, my tank is going to run out of water very quickly. You know, in fact, actually I can increase the amount of water. Maybe I can increase the initial storage to 200 cubic meters. But what is going to happen is that my consumption rate is is high compared to the amount of water that I have stored in the tank. So my system, the water in the tank is going to be used up very quickly. But I can still run this model at this stage. Let's run it and see what happens. So I'm going to run. So this is the simulation is done. Now what I can do is that I can look at, let's first look at the amount of water, maybe the storage inside my tank. So I'm going to right click on my tank 1, and then I'll click on storage, and what you see is basically the storage drops and basically runs out pretty quickly. Now let's see what happens to the flow. So basically I can look at the flow going out. So the flow initially is around 2,600, but it drops to 0 when my tank runs out of water. Basically the flow stops. I can also look at the use. For example, I can look at the use by this residential user. I can just right click on the link, and then I can click on flow rate. So what you see is initially when water is available, this consumer is using at a rate of 1,000 cubic meters per day, but then the water runs out, and then the use actually stops. Okay, so in order to prevent that from happening, I want to basically add a source of water to my tank. So what I'm going to do is that I'll first add a source of water. I'll use a fixed head boundary for that purpose, and then I'll add a pump to pump water from my water source to my tank. So what I'm going to do is first let me add this fixed head boundary. So this is a fixed head boundary, which in this case it serves as kind of my source water. It can be a lake, a river, something that has infinite amount of water available, so that its head doesn't change when we pump out. If you want to model a kind of a more realistic condition, when you have, I don't know, maybe you have a lake that has limited amount of water and we want to pump, we can actually replace this fixed head with an actual lake or a pond component in this case. So anyways, the fixed head boundary, I'm not going to change anything. There's an initial storage which is quite high. Now if I want to run this model over a very long period of time, that I'm concerned that this water may run out, then I can actually increase this. But in this case, I'm not going to do that. I'm going to run the model for a few days at most. So this is adequate amount of water. And the hydraulic head, I'm going to keep it. That's going to be the elevation of our source water. I'm going to keep it at 0. That will make things simpler. Next thing, what I'm going to do is that I'll add a pump. So basically, this is the pump that I'm going to add. So it's a pump with quadratic head flow relationship, and that's basically that's consistent with the head flow relationship that we have here. So this H is the head of the pump, and then we have this quadratic relationship between the head of the pump and the flow rate. So basically, let's just use that. The pump is actually a connector, so I have to connect my source water to my tank through this pump, and this link now it represents our pump. If I want to model the head loss in the pipe that carries water from the source water to the tank, then I need to add another junction and then another pump. I'm sorry, another pipe. I can also include the effect of somehow I can actually include the effect of the head loss in the pipe into my pump characteristic curve, which is basically the assumption that we make right here. So basically now let's indicate the characteristic curve. So if you look, it says that the equation that is used for a pump with quadratic head flow relationship, it looks like this. So we have an H0 minus an alpha times Q to the power beta. The beta value is 2. Basically, if you look at my equation, it's Q to the power 2. So I'm going to keep beta at 2. And then H0 will be 22. So I'm gonna make it 22. And then our alpha is going to be 1e minus 8. So let's see. So that's 1e minus 8, and that's according to my rating curve. And keep in mind that the unit, in terms of the units, this has to be consistent. So in this case, our Q is going to be cubic meters per day. That's always the case in OpenHydroQual because that's the day is our time unit. And then what it will give us is it'll give us the head of the pump in meters. Okay. So now with this, everything is set. The only thing is that I'm gonna run this model over a longer period of time than 1 day. By default, it'll run for 1 day, but I want to change that. So I'm gonna go to settings, solver settings. Oh, I'm sorry, general settings, and then I'm gonna change this end time. I'm gonna insert a numerical value, and I'm gonna change this to 5. So I'm gonna run this model for 5 days. Let me save it. Now I think everything is set. We can now run the model and get some results. So let me run it. So the simulation is done. Now let's look at some results. So basically, let's first look at the water depth in our tank. So if I click on water depth, initially it was 2 meters, and it dropped and reached to something around 1.6 or yeah 1.6 between 1.65 meters, and then it stayed there. So this is the depth where my the flow that the pump is pumping into the tank will be equal to all my consumption. So basically I can look at the total flow here. So as you can see, initially it's actually starts from a smaller value than the 6,000 that is our demand. The reason for that is that the head of the water in the tank is higher than the equilibrium head. So then we reach to an equilibrium where the flow that the pump is pumping into the system is going to be 6,000, and that's going to be how much we need. We can also look at the power of the pump. So this is the power of the pump in watts, which is calculated based on the flow rate and the head. Then next, let's do. Okay, we can now look at, I think things are pretty straightforward. We can look at the head of our nodes. That's something that you would be interested in if you want to design the network. You want to make sure that the head at these junctions are not basically below the elevation, or in other words, the pressure is not going to be negative, or the pressure is going to be acceptable. Actually, being negative, not being negative is not enough. You want to have some reasonable pressure. So basically what we can do is that we can look at the hydraulic head. So this is the hydraulic head of my junction 1, which is 15. It's a little higher than 15, and so this may not be adequate because if you remember the elevation is 15. So I have a little bit of head above what I need. Now I can look at another junction. Let's say here my junction 6, the hydraulic head is going to be 12.5. The elevation is 2, so I have adequate pressure right here. So I have some problem here in my junction 1. You can inspect other ones too. For example, maybe this one, I can look at the hydraulic head is 15, something around 16 meters, and my elevation was 12. So that may be enough or not, I don't know. But one thing I can do is that now I can go maybe and increase the diameter of this pipe to, let's say, a 20 centimeter pipe, and then I'm going to run the model again to see if that will improve the head at junction 1. So I can now look at the head. Now the head is higher, it's around 20, so I have around 5 meters of water head at my junction 2. That may be adequate. And this was it. Please look for my future videos, and thank you for watching.